Hello. Here we are continuing with the second application of the Biot-Savart's law where we wish to calculate or wish to determine the expression for the magnetic field intensity along the axis of a circular coil carrying current at a point along the axis. Now, for that, we'll be considering a circular coil first of all. Now, this would have been plane of the coil. If you see, the coil is uh, on the plane that I have drawn it. That is, let's say this is the x and the y axis, uh, and that is how we are representing. But we will be representing that plane to be perpendicular to the plane of the paper now. So it's actually somewhat like this. The look would be somewhat like this, a bit flatter circle. So that's more or less the way to look at it, a much more flatter way of drawing it so that you have and also a small gap for allowing the flow of current to get into the coil and then go out of it. So here we consider the coil to be carrying current in the counterclockwise direction, and the value of the current is I, and the plane, as you can see, is somewhat like this now is the y-axis. Now this is the x-axis over here that we were considering, and now this is the z-axis where we wish to determine the value of the magnetic field intensity. So the z-axis, which obviously in the other diagram I would like to show that the z-axis is acting out of the plane in that case, but here we have tilted or rather oriented the coil in a fashion where this is the positive x-axis, which was over here, that has gone inside somewhat. That is how you construct a three-dimensional figure in a two-dimensional plane. And this is the y-axis, and this is obviously the z-axis, on which, let us say, we are considering a point at a distance x from the center of the coil, and along that distance at that point P, we'll take it as P. So in that point P, we wish to determine the magnetic field intensity. For that, we would be considering two diametrically opposite lengths at the top and at the bottom as of now. So at the top and at the bottom, we'll consider dl length, uh, which obviously, as I have already mentioned in Biot-Savart's law, that they are directed along the direction of the flow of current. So in this case, while the current flows in the counterclockwise direction from the inside towards the outside rim of that circle that you see, so here it will be going out over like this, and here that will be acting somewhat inwards like that. So that is the direction of dl. I'll rather take this as dl dash because the directions are not the same, so it's wise from the vector perspective. Now I'll use another ink to show you the other parts of the figure. Now here, if we are to construct a position vector of the point P from that dl element, because that is necessary to apply the Biot-Savart's law. So here, that's the first of the position vector from the first elementary length that we have considered. Let that be equal to r vector, and from the dl dash element up to the point, that's again, let's say that's r prime vector. So you have the r and r prime vector. Now if we were to apply the Biot-Savart's law, we will be obtaining dB and dB prime due to both those diametrically opposite elements. And as far as the value goes, now dl and dl dash, obviously they are very small and they are nearly equal in magnitude, of course. So their moduli are going to be the same, and it's dl prime. And then again, you have this cross product. Now dl cross r vector, as you can see over there, that is perpendicular dl cross r, so that is going to be dlr times of sine 90, which is going to be 1. And if we do the cross product over there, you now had the r vector or the dl cross r, had that been somewhat like this, dl and r on the same plane, on this kind of a plane, you would have obtained the cross product of it perpendicular like this. But here in this case, as you can see, dl goes like that, but r is tilted, and the plane is tilted from the vertical. So this vector would, which would have been completely normal to what, as you see it, this vector would be tilted by the same angle theta from which this r vector is tilted. So you will get the product along this direction, which is going to make an angle of theta from the vertical. So in this case, you are going to get the dB along this direction, which is perpendicular to the plane containing both dl and r. So this is dB vector, which again is going to make an angle of theta with respect to the y-axis. And then also for the dl primed element, the dB is going to act in the downward direction, dB prime in this case, and that is also going to make an angle theta with respect to the y-axis. Now with those uh, angles taken into account, you have the cosine component of uh, each of those fields, dB cosine theta and dB prime cosine theta, to be acting exactly in opposite directions. Now this angle theta that you see is also equal to this angle theta over here, that the position vector makes with respect to the horizontal z-axis in this case. So from that, what we get is we get two of those sine components, that is dB and dB prime's sine component. So dB sine component acts along the same direction as dB primed sine component, that is sine of the angle of theta, and both of them will add up because they are along the same direction. So both of them will add up, and they would be responsible to give the resultant of those of that net magnetic field, or the resultant magnetic field in that case, while the cosine components cancel out. Now why do they cancel out? Because dB and dB prime, again, they will have the same magnitude. Let's see what is their magnitude in the first place. So if we were to consider the magnitude of dB first up, then we have dB is equal to, as far as Biot-Savart's law is concerned, we are going to apply that dB is equal to mu naught over 4 pi I dl, that's the element, dl sine of theta in this case, as I said, is the angle between dl and r, which is 90 degrees in this case. So sine 90 goes to 1 over the square of the distance, which is r squared, and dB prime is also the same thing. In case of magnitude, we are concerned about the magnitude in this case, I dl, and again dl dash, as I said, is equal to dl over here. I mentioned that. So this is also sine 90, and down there, and then the r and r prime, obviously they are going to be the same because the distances have been taken, because the point P lies along the axis of the coil, so the distances are going to be the same. um, r prime squared r and r prime squared r, or r and r prime, are equal in magnitude, so their squares will obviously be equal in magnitude. So these two factors, they are bound to remain equal in magnitude, and that is why with the angle being the common case, being the common value, uh, that is theta, both of them cancel out the cosine components. So that is the reason we considered the diametrically opposite components, because uh, with these diametrically opposite points or elements considered, they are going to cancel out each other every time we integrate from one end to the other. We will be integrating dl along this line right till the bottommost point, and then dl prime will be integrated up to the topmost point, and in that case we'll be covering the entire circle. So because I have already drawn the diagram and I have already explained, so doesn't really matter if the doesn't look good now. So now we know that the resultant magnetic field, which is the net magnetic field, will have its magnitude to be acting along that direction. That direction is fixed, so that is along the positive z-axis when the current is flowing in the counterclockwise direction. So we'll again be discussing about the direction once again. So dB net is equal to 2 times of dB sine theta. I can say that dB is equal to dB prime, and I can take it as simply as dB. So 2 times of dB sine theta, which I obtained out of this, and then we have 2 times of, I put the value of dB over there, that is mu naught I over 4 pi r squared, and dl is there, and there is a sine theta, of course. Now from that triangle that we see, let's have the center of the coil at O, and this topmost point, let us say that is some point M. So OMP, I'm redrawing that. So this is the center of the circular coil. M is the point where the dl element has been considered, and this is equal to, and this is the position vector r. So, and as I mentioned, this is the angle theta. So this angle theta will have its sine value to be equal to OM over, and this is the point P, of course, OM over MP. Now OM is the radius of the circle. Let's say the radius of the circle is A in this case. So we have the radius as A, this distance as X. So this is A over R. So we have to get cancelled with the 4, so mu naught times of I over 2 pi, and then there is r squared, and then we have a over r for sine theta, and the is integrated dl is integrated from 0 through to half of the circumference, because we have considered two elements, so each element going half of the circumference completes the entire coil. So we need not take 2 pi a, the 2 factor was already over here, so we need not be concerned about that. So now we end up with mu naught I over 2 pi r cube, and there's an a over here, and integrating this we get pi a. So finally one of the pi's get cancelled out, and we have mu naught I a squared over 2 r cube. If we put the value of r explicitly over here, then we get mu naught times of I a squared. Now what is the value of r? Where r is equal to a squared plus x squared under root. So a squared plus x squared under root, and then taken the cube of that, so this is 3 over 2. So this is the value that I obtained. However, it may look pretty dangerous over here, but we can just get the essence of this equation by considering another case. Well, the case is that if I consider x to be equal to 0, that is the axial distance to be 0, then that point P that we saw over here, that will coincide with the center of the circle. That is x being 0, P coincides with the point O, which is actually the center of the circle. So now we are trying to find the magnetic field at the center of the circular coil, which is carrying current. Now, for that, we have x is equal to 0 over here, and if we put the value of x to be equal to 0, then we get the value as mu naught times of I. This is the value of b now, which is mu naught times of I times of a squared. Now x is equal to 0 in the denominator, so we are left with a squared, and in the power term we have 3 over 2, so a squared 3 over 2 means a, the power terms multiply, 2 and 2 cancels out, so a cube, and you have an a square at the top that cancels out with two of the a's in the denominator, so you are left with mu naught I over 2a. Now remember, the direction remains as such, even if you have the, because the direction is as per the Biot-Savart's law, the law remains intact, only the values or the magnitudes have changed. So we have this direction to be acting into that coil that I had done. You will have to go back in the video to actually view the coil properly. Now it has been destroyed, demolished by me. So okay, I'm redrawing it once again. So this is the coil, this is the center of the coil, and now the magnetic field, as you can see over here, not directed into, actually it's directed out of the coil, my bad. This was directed, the two of the components were directed to the right hand side along the positive z axis. The direction remains intact. Now with the current flowing in the counterclockwise direction, the direction remains intact for the magnetic field, so it still acts along that direction, right? So that's the direction of the magnetic field. However, the magnitude has changed, or we can say the magnitude has actually increased because the denominator term has reduced. With the value of x reducing, the denominator has reduced. Now if I were to construct uh, if I were to construct a graph showing the variation of the magnetic field with respect to the distance, I'll consider the distance on either side of the coil. Then uh, because it's the axis of the coil which is extending on either side, it's only the direction of the magnetic field that is changing. So we can actually consider the magnetic field in terms of magnitude of the magnetic field, just the magnitude, not the vector wise, because the vector wise direction would be completely opposite. So just for the sake of for the sake of magnitude, it has the highest magnitude when x is equal to 0, is the variation of x along that axis. So, and that magnitude being this one, mu naught I over 2a, a being the radius in this case. And then it reduces exponentially, and it shows an asymptotic nature, uh, where it will meet the x-axis or the x value uh, in the uh, at infinity. So that's the case of magnitude of the magnetic field varying with the distance along the axial line. Now I have taken this, although that is the z-axis, and I have taken the value as x, so that's not to be confused. This is the x-axis, but here the value has been taken as x. I could have taken it as z, but I'll be using that x. I have actually used that x, and I'll be using that x once again later, when I'll be comparing this magnetic dipole with that. When I'll be comparing this coil with the magnetic dipole. So that's for later. In fact, I have done that in my magnetism part. You can check for yourself, but we'll be redoing that once again in this chapter. So this shows the magnetic field intensity that is associated with a circular coil along its axis. There are also few cases that we must consider on about which I have tried a few numericals in my neat corner. You can check that, where I have considered a semicircular coil Now, for n number of turns of each in this coil, you will be getting the magnetic field to get multiplied by n times for n number of turns. Here also you will multiply a factor n for n number of turns, because each turn will be giving the magnetic field along the same direction, and each of those magnetic field is going to get added for the direction being the same. Now, if I were to consider an arc instead of the entire circle, which is subtending a certain angle theta to the center, then the magnetic field intensity in this case would have been by unitary method, you can say that it is mu naught I over 2a for the entire circle, but now it's theta over 2 pi when theta is taken in radians, or theta over 360 degrees when it is taken in degrees. So that's the case of magnetic field associated with an arc length of a coil carrying current. And of course, as far as the direction is concerned, if you are getting the direction to be out of the plane of the coil in case of a counterclockwise current flowing through the conductor, you'll be getting the current, you'll be getting the magnetic field to be directed into the plane in case of a clockwise motion of the current, and that is the Snow rule. Let me use a bit of space over here only. So this is the face of the circular coil that we are observing. And if the current is flowing in the counterclockwise direction, then it would represent a north pole. And because the lines of force or the magnetic field will be directed out of it, which is what I have done in this case, the figure that I have shown, which was there initially. And then if we are considering a clockwise motion of the current, then the case would be that of a south pole, where the lines of force or the magnetic field is directed into the plane. So this is more or less the case of the Snow rule, where the S and N lie within that O, that is the circular coil, and it's easier to remember in this way. So you can compare it to the magnetic dipole, and then predict the direction. So you have the direction already. And the only thing that you need to do is obtain the expression, which is quite gettable by using Biot-Savart's law as we saw it. So that's more or less about this video. I'll be doing a few numericals related to that. Related to this, I have done a few numericals already. In the neat corner, you can check for yourself. We'll do some more bits on this, but that is to be dealt with in the other videos, upcoming videos. Till then, thank you for watching.